Well, yeah, it's obviously both a pleasure and a sadness to be here today. My name's Peter Turner. I was one of David's PhD students between 2000 and 2005. Yeah, again, pass on condolences to the family, and it's great to see everyone, at least virtually. I wish I could be there in person, but it didn't work out coming to you from Sydney, Australia right now. But I will be back finally. First time back in Canada after a few crazy years in August, so I hope we will see some of you then. Yeah, I've put together a presentation on some work. Let me try to share that now. I hope this works. Just a moment, sorry. So it looks like, apologies, I might have to restart the Zoom here. Is that visible?
Yeah.
Yeah? Great, good. Sorry. Yeah, I'm going to talk about something maybe a little bit different. So as I say, I was one of David's PhD students. We worked in obviously mathematical physics with applications in nuclear physics. You're going to hear, I think, several amazing talks from that aspect. I think fair to say David's first love or loves. Like I say, finished in 2005 and went more in quantum information and quantum optics direction. So that's what I'm going to be talking about today, but how some of David and other people, I believe, that are in the meeting today, their work applies in this area. So to start off, I think we saw this photo or a piece of it in the slideshow just now. This is the summer of 2000. In the office on the 9th floor of the McLennan Physics Laboratories. This is the office that I came into.
We're not seeing your photo. Have you switched?
I have switched.
So have you got multiple displays?
No. So you could see the first one, but you're not seeing it now. Is that right?
We see the opening slide of your PDF. There we go.
Okay, so it's the full screen view that might be the problem. So you might have to tolerate the border there. Is that visible though for everyone?
Yeah.
Yeah.
Yes.
Okay. Yeah, we saw this photo in the slideshow. As I was saying, this is the office I came into in 2000. That's Sarah Karam, a summer student on the left, Juliana Carvalho, Joe Repka, David, of course, Steve Bartlett, and Kyrul. Several of us, Kyrul Bahri, pardon me. Several of us, I believe, are in this meeting or speaking at this meeting. I was away that day, and this is the early days of from my perspective, of computers, and I was so desperate to be in the photo that Steve and I did a Photoshop of myself in there, and you can see I was always trying to get closer to David, even back then. So there's a couple of more here. This is lunch in Chinatown, Toronto, with myself, Joe and Debbie, David, Gabriela Tiamova, and Shen Yong, I think, is speaking after myself. This is probably around 2005. And then one more a few years later, a reunion with Shen Yong, Steve Bartlett, and myself, of course, David in the back left, and Helen Friedoff and Terry Rudolph, two colleagues at the University of Toronto as well, or York University. For Helen, in Helen's case. This photo is probably 2013 or something like that. And I saw David in 2019 in my last trip to Toronto, and he insisted on walking to the university to come and see me for lunch. So I was very happy to be able to see him. All right, I should get into it. So I'm going to be talking about unitary-unitary duality, and this is a theme, I think, in a lot of David's work. This is a review paper from 2012 with David and Juliana and Joe, where you can read much more about all of this. And it's a combination of that in this paper. I'm not sure if Ephraim is in the audience, but when I was at the end of my PhD, one of Ephraim's students approached me about a problem they were having in the quantum optics lab down there, and this work goes all the way back to then. And I spoke to David about this when I was just finishing my PhD. To him, it was all obvious, and I'm sure it was at the time. It took me quite a while to wrap my head around some of these things, but that's the story I'll be telling. And it takes us to things that you might have heard of nowadays in the quantum information world, quantum computational supremacy and quantum computers and boson sampling and all this kind of stuff. So there's a connection being made to some work, really quite high profile work. And the one on the right there is a review or a letter written by Barry Sanders, who I think will be speaking later today as well. So this all stems from quantum interference, one of the fundamental signatures of quantum mechanical behavior. This in particular in photonics is probably best represented, or the prototypical example is the hongo mandel effect, 1987 interferometry paper, where you see this dip in the coincidence counts as you put photons simultaneously into two arms of a balanced beam splitter. And the dip happens as you change the timing of those photons. When they're not at the same time, they're distinguishable by their timing. And you see the coincidences, and that's the line, the horizontal line. And then as you move the timing of these photons so that they are simultaneous, they become indistinguishable. Nature allows them to interfere, and you see the coincidences go down, which is something that wouldn't happen with classical particles. So this is a very famous experiment, and like I say, it leads to nowadays things in quantum computing and demonstrations of what they call quantum supremacy, where they show that there are quantum devices that cannot be simulated by even the best supercomputers on Earth nowadays. So to remind us of how this hongo mandel effect works, we've got two photons in two modes, and I'm using capital N for the number of particles and a little d for the number of modes. These don't have to be photons in the grand scheme of things, but that's the example we're going for. I'm using spin notation, maybe frustratingly, for the top and bottom modes. We've got creation operators for these two photons, and coincidence state means I put one in the top mode and one in the bottom mode acting on the vacuum. My balanced beam splitter is represented in this case in the fundamental representation of SU2. You can either do it in several different ways depending on your phase conventions in the lab. But the bottom line is, if it's balanced, as these photons evolve through the beam splitter, they become these linear combinations, and you get this cancellation of the cross terms in the middle, which would not happen classically, as we say. And that means the coincidences are suppressed. You don't see the up-down outcome anymore. You just see the up-up outcome or the down-down outcome. So if you think of these, there's an analogy with coins and flipping coins and whatnot in classical mechanics, and this just wouldn't happen classically. This is a quantum mechanical effect. In real life, that was very ideal treatment of the situation. In real life, there are many other modes in the universe that these photons and degrees of freedom that these photons can have. I've talked about their timing before. It could be their wavelength and frequency. It could be their spatial mode. It could be all sorts of different things. So we add an extra label to these creation operators to keep track of these extra modes. So I'm calling S the system mode. This is the mode that the interferometer, the degree of freedom that the interferometer is acting on. This is the thing that we control in this experiment, usually the spatial modes for these photons. And L, I'm using L for a label mode. This is just some other degrees of freedom, whatever they are, these particles, in this case photons, that are going to serve to distinguish them in the long run or not. In the hongo mandel experiment, it's timing that does the distinguishing, that is the label. So I'll do early and late, or left arrow and right arrow for those two possibilities. You can set this up all sorts of different ways. And we only need two. In this case, we have two particles. We only need two modes in order to keep track of those things, in order to label them. In this case, everything's equal to 2, the number of particles, the number of system modes, and the number of label modes. And now I've got an indistinguishable state where they're both in the same label mode, say early, and I'm representing that now as a Fock array. So Fock state occupation numbers written in an array, where the rows are the system modes and the columns are the label modes, and these are in the same column, so they are indistinguishable in this case. They have the same label state. Whereas if I want to do a distinguishable state, then it's hopefully clear that I would put one of the photons, say, late, and it becomes it sits in a different column. And there we have. So this is a way to model distinguishability, and it's going to turn out that distinguishability comes out as correlations between the system and label modes. So if you do quantum information, you do this kind of thing, a lot of entanglement and correlation between different degrees of freedom or different tensor products in a tensor product structure, whatever you got, in this case, the system and the label. And you want to trace those out, those environmental modes, those label modes, those other modes that you don't control, you often want to trace out to do mixed state analysis. But in the second quantized Fock state picture, that tensor product structure isn't available to be traced out. You've got this kind of structure, a harmonic. You've got ds times dl, in this case 4 harmonic oscillators. It's not a simple tensor product between the system and the label degrees of freedom. So that's motivation to go to first quantization, which is something that is rarely done, I think, in quantum optics. But this is really where you see this unitary-unitary duality that David and others have worked on in the past so clearly. So the connection between first and second quantization, of course, is symmetrization. So this indistinguishable state, for example, I can write it in the particle picture. I've got one photon that is up and early, and I've got another photon that is down and early. And I symmetrize over the particle numbers, this imaginary particle numbers 1 and 2 that I've used there to get the second line. The third line is just I just reorganize the tensor product structure. Now I split up the system and the label tensor product, which I can do. So it's just rewriting the second line, binning, if you like, the different degrees of freedom. And now in the fourth line, I've written this in group theory notation for those of us who I'm sure appreciate that kind of thing. That's a fun joke in some of the rest of the physics community, where I show people things like this and they say, your LaTeX fonts are broken. They don't see a lot of Young diagrams in experimental, for example, quantum optics papers, but that of course is this way to write those symmetric states. So and then you can do this similarly for the distinguishable case, and you can see very, very clearly in the indistinguishable case, that's a separable state. There is no entanglement. There is no correlation between the system and the label. Whereas in the distinguishable case, that has Schmidt rank 2. I can't write that as a separable state. And that is, of course, exactly what's going on. If you're a quantum information person, you now can trace out that label and get these mixed states represented by these density matrices, the indistinguishable case. And the distinguishable case, I can now pull out my quantum information textbook and do this whole analysis, the same hongo analysis in first quantization, write down my measurement operators, write down the unitary corresponding to the interferometer, but now in the 2 photon representation, which these are 2 particles with 2 degrees with 2 states available to each of them. So this is singlet triplet stuff. And I'll talk about maybe the permanent and determinant business a little bit later, if possible. And I can just do this calculation, and I get, of course, the same answer. If the input state is indistinguishable, the scattering amplitude to go to coincidence goes as the permanent of that matrix squared. Whereas if there's a distinguishable state going in, then that determinant shows up. It's a very curious mathematical fact that I can't understand, how that becomes the sum of these 2, permanent and determinant squared, becomes the permanent of a square of U. But we can talk about that later on if there's time. And you plug in the balance beam splitter and you get the Hom dip. So this is a first quantized analysis of the classic Hom experiment, but I hope it illustrates how these duality aspects come in, and that's what I'll just emphasize now. I'm sure most of the experts in the audience know this quite well, but what we're really doing, one way to look at it is we're Schur-Weil decomposing each of those 2 degrees of freedom separately. So to remind us, Schur-Weil factor, if you like. I can decompose the Hilbert space of n, what we would say in quantum information, n q dits, n d level particles, into the direct sum of tensor products of a unitary and symmetric group representations. And certainly in quantum information, this is fairly well known, and we use lambda, p, and q to index these things. Lambda is indexing the irreps. P and q are indices into those unitary and symmetric group irreps. I think I've mixed up my standard and my semi-standard Young tableau there, but that's a typo. As we saw in the last case, there's correspondence between Fock numbers and the unitary weights for the symmetric states. And in fact, this goes deeper. We can get into that more if anyone's interested as well. If there's more particles and you've got intermultiplicities, you can keep track of these with another index. But I'll leave that aside. And now to get to the unitary-unitary duality, I look at it as a coupling problem, basically. I've got 2 degrees of freedom. I sure can decompose both of them. And I ask, how do I couple 2 systems with symmetric symmetry, good permutation quantum numbers? How do I couple these 2 systems to make kind of a permutation scalar? And it's very much like angular momentum coupling. The Clebsch coefficients are all equal and they have the same sign. And in fact, if you go into that paper that I flashed up at the beginning, David, Joe, and Juliana, this is one way to prove the unitary-unitary duality. So the point here is that this generalizes entirely. It is exact, and it is completely general. So for any number of particles in any number of modes, you could model distinguishability in quantum mechanics this way. In this case, for bosons, we're going to look at the symmetric subspace, or the symmetric space of these 2 degrees of freedom for n particles. But of course, if these were fermions, we'd look at the antisymmetric subspace, and everything is very, very similar. So you can use this to do things, and I guess I wanted to introduce, just in case anyone in their travels comes across a couple of David's academic grandchildren. These are students of mine from the University of Bristol, where I was just before I came to Australia and COVID and all this craziness. But Staja Stanisic worked on this kind of thing using this approach to generalize the hongo mandel effect to as many particles as you want and in as many modes as you want. Of course, it's a difficult problem computationally. Because it is exact, all of the complication is preserved, but Staja is quite a ninja with numerical optimization. And we came up with for up to 8 photons, you can kind of have numerical evidence for the optimal type of interferometer you would use to identify different types of distinguishability that these particles can have. And the other way is another direction that you can go is now you've got this connection between the Schur transform, the Schur-Weil duality, and the boson sampling problem, because the boson sampling problem is about chucking a whole bunch of photons into a big interferometer and trying to sample from the distribution that comes out. We've now made that connection, and there are known efficient quantum circuits for the Schur transform if we ever do build a quantum computer. And this work makes it clear on how you could introduce noise into those kinds of circuits in order to model realistic boson sampling experiments. And in fact, you can use this technique to improve classical simulations of boson sampling, which is something that a second of David's academic grandchildren, Alexandra Moylet, and I worked on a few years ago as well. So I'm not sure how much time I have. I'm just going to wrap up fairly soon, I think. I guess maybe I'll just point out this. I mentioned the permanent and the determinant business. This is something I've been thinking about a lot, and I know Hubert and others have as well over the last few years. When I saw the boson sampling paper from 2011, you see this construction. The boson sampling paper was Aronson and Arkhipov, and this construction goes back in several directions, many years, but it was popularized, at least in this case, by them. And it's this fact that when you have non-interacting bosons, you take the scattering, the unitary describing the interferometer, a d by d matrix for a d mode interferometer. You construct the d by n matrix by repeating the ith column of u n I times, where ni is the input Fock state that you're putting into the interferometer. Then you take that matrix, which is rectangular, and you construct the n by n matrix by repeating the jth row of that matrix mj times, where m is the output Fock state that you're trying to compute the amplitude of scattering into. And then the scattering amplitude for that process is the permanence of that matrix W that you've just constructed with some normalization there. When I saw this, I said, wow, that's knowing through David and many of us understanding the connection between the representation theory and in this case, the photonics. Wow, that's a construction of the symmetric representation of the unitary group that I've never seen before. And I wonder if it just begs to be generalized to irreps that are not the symmetric one-rowed Young diagram. Again, it was David who recommended Wyburn's book to me, and I was reading it back then, and this is just something I stumbled on, where this is from a website that the quantum information community often goes to, where coincidentally someone in that community had discovered immanence in a totally different context. And I remember writing this now in that time saying there must be some connection between these immanence and the boson amplitude, the scattering problem. And I didn't have time to work on it, as I said there. And finally, over many, many years since then, I've started to work on it now. So, and like I say, Hubert and others have. So it's a tough problem, and be very happy to talk to others about it. I know Joe Repka, if you're there, I've bothered you about it in the past, and again, Hubert's worked on it. But yeah, yet again, David helped in pointing me in the right direction there, as he did so many times during my research career. I'd like to wrap up. I think I just wanted to add, again, we're I think looking at the list of great speakers and great topics, we're going to hear a lot of nuclear physics and mathematical physics, was, like I say, of course, David's bread and butter. But I guess wanted to kick things off and make it clear to everyone how far-reaching David's work went outside of those fields. And maybe there's from my perspective, one of the best examples of this is another paper. This is in the Canadian Journal of Physics in 1978. David gave me a hard copy of this paper, which we don't get anymore. So it's quite dear to me. It sits on my shelf just above me here. Where David essentially kind of for himself, I don't want to say discovered, because all this stuff was happening around the same time. I think I'm sure there are others in the audience who know the stories better than I do. But if you're familiar with squeezing in quantum optics, one of the fundamental, really kind of driven the whole growth of quantum optics in the last 40 years, David wrote this paper in 1978, kind of giving his take on the squeezing phenomenon, again using this algebraic approach and the mathematical physics approach that he knew so well, and really pioneered so many techniques in. So this is a very special paper, worth reminding people about in a field outside of the regular one that David would work in. So I think with that, I'll say thank you again, and again, I wish I could be there in person. But it is great to see people online, and just say thanks very much.
So got about 5 or 6 minutes left if people want to ask questions or just